How would you teach a computer to recognize a dog? If you show it a dog running through a park like this one, you and I instantly know what we're looking at. But a computer just sees a grid of millions of colored pixels. For decades, the traditional approach was to provide the computer with a rigid set of manual instructions. You would write code that says, if the object has 4 legs, and if it has fur, and if it has a snout, then output the word dog. But watch what happens when we show that program a cat. The cat also has 4 legs, fur, and a snout. Because it checks every box on our list, the computer follows the logic straight to the incorrect label. The real world is full of these exceptions. A 3-legged dog or a puppy partially hidden behind a bush will break the logic immediately because they no longer fit the hard-coded rules. To fix this, you would have to write a unique rule for every possible variation in angle, lighting, and shape. This leads to a combinatorial explosion, a web of instructions so massive that it becomes mathematically impossible for a human to manage. This mechanical approach to logic works for math, but it fails in the messy ambiguity of our daily lives. To move forward, we had to stop trying to write the rules ourselves and build machines that could learn from their own experience. Instead of a list of rules, we give the computer a new goal. Look at thousands of examples, make a guess, and refine that guess based on the results. To make a good guess, the system has to figure out which parts of an image actually matter. It has to separate the defining traits of an animal from irrelevant details in the background. Think of it as giving the machine internal dials to prioritize information. It can turn up the importance for pointy ears, while it turns down the importance for green grass. These internal dials are the weights. By adjusting them, the system builds its own intuition about which features are the most reliable clues. Even with the dials set perfectly, the machine might still be a little too hesitant to make a decision, or a little too eager to scream "dog" at the slightest hint of fur. To control this, we add a baseline that shifts the starting point for every decision. This makes it easier or harder for the incoming signals to cross the finish line and trigger a final guess. This adjustable baseline is the bias, and it provides the mathematical flexibility the system needs to finalize its internal debate. When the machine inevitably gets an answer wrong, outputting dog for an image of a cat, it uses that failure as a training signal. The machine identifies the error and traces it backwards through the math. It looks at the specific path it took to see exactly which weights and biases contributed to the wrong answer. This reverse correction is backpropagation, the fundamental mechanism that allows the system to fine-tune its internal dials after every mistake. Because a machine might have millions of these internal dials, spinning them randomly through trial and error would take years of computing power. Instead, the system uses a mathematical compass to reduce the size of the error. It calculates the quickest way down this slope toward the lowest point, where the error is 0, and adjusts every dial in that specific direction. This mathematical optimization strategy is known as gradient descent. It turns what would be an endless guessing game into a practical process where the computer reaches high accuracy in minutes rather than days. When we stack thousands of these individual decision makers together, they form a multi-layered web, where the output of one node becomes the input for the next. This structure mirrors the biology of the human brain. Just as our own neurons fire electrical pulses only when they receive a strong enough stimulus, these mathematical nodes only signal the next layer when their combined weights and biases cross a specific threshold. This interconnected web of learning nodes is the neural network, the backbone of modern artificial intelligence. We finally solved the problem of real-world ambiguity, not by writing the perfect rules, but by building a machine capable of discovering those rules on its own.